Now, the first model that we are going to examine is MM1 model or single channel model. And as you can see here, there's one channel, one queue, and there are waiting lines. And here's your arrival rate. And here's your service facility. You have only one server, and this one is taking care of all these demands. And that's a basic model that we need to look at. And then after understanding this, we will expand it into different situations. Single channel model or single channel, single phase model considered here is one of the most widely used and simplest queuing models. It involves assuming that seven conditions exist. First, arrivals are served on a five-fold basis. Every arrival waits to be served. There's no balking or reneging. Arrivals are independent of preceding arrivals. That's the third one. And fourth one is arrivals are described by Poisson probability distribution and come from an infinite or very large population. And fifth, service times also vary from one customer to the next and are independent of one another. And the average is known. That's a fifth assumption. Sixth assumption is service time occur according to the negative exponential probability distribution. Seventh one is the average service rate is greater than the average arrival rate. And given these assumptions, scholars and mathematicians and statisticians have diligently worked on this model and found that these formulas to find various indicators of waiting lines. For example, the average number of customers or units in the system is noted by L. L equals lambda over mu minus lambda. Here, lambda means the arrival rate, how many people are coming in, like 10 customers per hour or per minute. That can be 10. Or mu is, how many people or demands a service or a server can take care of and process. There are 10 customers and you can process 20 people in an hour, then it's a very efficient situation. However, if your mu is only 5, when your demand is 10, then you are going to incur more people waiting for you, right? So it's not a good situation because your line is going to increase more and more. The second topic, the second statistic is LQ. This is similar to L, and the average number of customers in the queue. So this shows how many customers are in the queue that is being shown here. The third one is the average time a customer spends in the system. So this is wait time, it's a W, and that's why it is being used. WQ is the average time a customer spends waiting in the queue, that's WQ. And fifth one is the utilization factor for the system row, the probability the service facility is being used, right? So how much it is being occupied by the service, that's shown by row. And P0 is the idle time. What is the probability where no customer is being served in the system? That's a P0, which is 1 minus lambda over mu. And the seventh statistics PNK is the probability that the number of customers in the system is greater than K, or P n is greater than K. And that's a complex formula that we have to use to calculate this. Let us now take an example to to understand this MM1 module. Let us apply these formulas that we have learned to the case of Arnold Muffler Shop in New Orleans. Arnold's mechanic, Ride Blank, is able to install new mufflers at an average rate of 3 per hour. In other words, the mu is 3 per hour, which is about 20 minutes customers needing this service arrive at the shop on the average of two per hour. So two cars are arriving per hour into this shop. And Larry Arnold, the shop owner, feels that all seven of the conditions for a single channel model are met, and he proceeds to calculate the numerical values of the preceding operating characteristics and found them as shown. So the first one, the two cars in the system on average is in there, and the wait time is 1 hour that on average car spends in the system, and LQ is 1.33 cars waiting in line on average in the queue. That's what they found. And the fourth one is about 40 minutes. WQ is 40 minutes average waiting time per car. So in the system, that's what is happening. And the row is 2 over 3 is 67%. So 67% of the time mechanic is busy. The utilization rate is that 60-70% of the time the mechanic is working in the system. And the P0, again, that is the probability that there will be no car in the system, and that's 33%. So there's a 33% of chance of not having any car in the system. And lastly, here is the probability of more than k cars in the system. So there is a more than zero cars, 67%, more than one car, 44%, more than two car, 29.6%, more than three car, about 19.8%, more than four cars, 13%, more than five cars, that's less than 10%, and so forth. So that can be calculated here using the formula that we learned. And then we need to also understand the total service cost and total cost that you are incurring through this shop. So the total cost is defined as number of channels times cost per channel, right? So one channel, how much does it incur to service your customers? That's what it means by total service cost. And we have M. M is a number of channels, and in our case, we have only one channel, so M is 1. And CS is service cost of each channel. So how much does it cost to have the line running? In this case, how many, you are hiring one person to work for your line, and how much do you pay for it, right? So that's going to be your service cost. And another thing that you need to look at is total waiting cost. So by making your customers wait for your service to be taken care of, how much are you paying for it, right? So that's the cost that you have to consider too. Obviously, the longer you make your customers wait for your service, the worse it is. And it can be calculated by this formula. Total time spent waiting by all arrivals multiplied by cost of waiting, right? So what is the cost of waiting and how much time do they wait? And that equals number of arrivals. So how many arrivals you have multiplied by average wait per arrival multiplied by CW, waiting time. And that is summarized here as total waiting cost will be lambda times W times cost of waiting. So W is wait time, lambda is the number of people coming in per hour or per day, and the CW, the cost is there. And total waiting cost will be J lambda times WQ times CW. That's another way of calculating it. So then the total cost will be this cost, total service cost plus total waiting cost. So MCS plus lambda times W times CW, that's going to give you total cost. So then let's apply that formula to Arnold Muffler's shop, and total daily waiting time it's a daily, right? It's not hourly waiting cost. So they have 8 hours per day usually, and lambda was given as 2 cars per hour, and WQ we found that it's a 2/3, and CW, the cost of waiting, is given as 50 here, so the total cost will be total waiting cost will be $533.33 per day, right? That's how you can find the total daily waiting cost. And the second thing is total daily service cost. And we learned that the mechanic's wage is only $15 per hour. That's too low, but let's use that. And that's 8 hours per day times the number of channel. We have only one channel, and CS is $15. It's given there. If you calculate that, $120 per day you are paying the mechanic. And if you add them up together, then 533 plus 120 gives you 653 dollars and 33 cents. That's your total daily cost of the queuing system, which includes waiting cost and service cost together. Now let's think about another situation. What if Arnold wants to hire a different mechanic with a higher efficiency than the current mechanic? Say that person can fix 4 cars per hour rather than 3 cars. So his efficiency is better than or higher than the previous or current mechanic. However, the demand is the same. Lambda equals 2. That's the same. So in that case, would it be better? If it's better, how much money can he save? That's given that the demand is the same, but you are kind of hiring a person with a higher efficiency by paying more money to that person, to the mechanic. So would that save you money or not? If so, how much, right? That you want to know. And let's apply this formula using these two dimensions. And then we find that the wait time, the length of the line is 1 hour in the system, and wait time is of a half hour, 30 minutes that a car spends in the system. LQ is half car, so length of the queue is half car waiting in line on average. So not even 1 car, only half car. So it's fantastic situation. The waiting time in the queue is usually 1/4 hour or 15 minutes on average. So that's what we find. So which is really good. And S5 is raw, and that's 50% of utilization of the mechanic. So 50% of the time he's always busy. And the sixth one is P0, the idle time is about 50% of the chance of the idle time you have. And lastly, the probability that you are going to have, about 0 cars or 1 cars or more than 2 cars and so forth are the same as before. So we find that. Now let's calculate the total cost. The total cost, if you do the same calculation as before, then you find that the waiting cost is $200, and you are paying about, you paid $120 to the previous or the current mechanic, but if you hire this person $160, however, you significantly saved the waiting cost, and in total $360. So if we compare, before it was $653.33, and now you are incurring $360. Therefore, almost $320 of savings you are going to be making by hiring this person and firing the current mechanic. So I think it's a good deal, right? Now let us do this calculation together using Excel.